There you go, Dean.
Okay. Thanks, Charlie. It's my pleasure to introduce Dr. Lewis McCaffery tonight. Lou has been a long time presenter at the Watershed Education Series. He's developed a reputation for presenting solid material that's useful. He does it in a way that's friendly and very easy to understand. Every now and then he'll even throw a little humor in to pick the activity up as the presentation goes along. And he does a lot of work around the lake. In fact, he's been known to do water sampling through the ice in the winter. And one of the reasons you can tell that he's a very valuable DEC employee, they require him to wear an emergency suit when he goes out on the ice. In case he breaks through, we won't lose him. So with that bit of my humor, I'll turn it over to Lou and let him introduce his program for tonight.
And it looks like he's muted.
Unmute.
Okay, can you hear me now?
Yep.
Yep.
And can you see my screen now?
Yes, we can.
Okay. All right. Well, thank you everyone for coming tonight. And thank you for that introduction, Jean. So I am going to talk about Conesus Lake water quality, and I'm going to be talking about the results of the CSLAP volunteer program, and I'm also going to talk about the Winter Limnology program that Jean touched on. So as way of an introduction, I wanted to make you aware of the little unit that I work in. It's called the Finger Lakes Watershed Hub. It's called a hub because it covers two separate DEC regions. And those regions are Region 7 over around Syracuse, and Region 8, of course, with the Avon office as its headquarters. So it was set up in 2017, mostly in response to some cyanotoxins which had been detected in the water supply of Auburn, and that was coming from Owasco Lake. And it was definitely a wake-up call. And so we are focused on water quality in the Finger Lakes. But sometimes we are called to do things outside of the Finger Lakes. So for instance, today I'm talking to you from the town of Lyons Falls, which small little place in between the Tug Hill and the Adirondacks. And I'm out helping my colleagues in the stream section with some of their sampling. So we do get pulled in various different directions. We work on lots of lakes, but of course the most beautiful and the most important lake is Conesus. I'm sure you'll all agree. Just a couple of pictures here. These are the original colleagues, myself, Amy Klinkhammer, Scott Cook, who many of you will probably remember. He's now retired, but I can pass on that he is having a lovely retirement fishing on Cayuga Lake. And Tony Prestigiacomo. Down there is me having to try and recover a logger that we unfortunately lost in Seneca Lake. A little bit of midsummer sampling on Canandaigua Lake. And this was a picture of my colleagues using a huge old Monarch, it's almost cast aluminum boat out on Conesus Lake. And this was in April 2000, just a month after the start of the pandemic. So we had to, we wanted to continue with our sampling, but we were all fully masked up. All right, so CSLAP is a really important project or program for us in DEC. And I'm just going to explain what it is, because we're going to be looking at some of the graphs based on this project. So CSLAP stands for Citizens Statewide Lake Assessment Program. And it had sporadically been operated in the Finger Lakes since its inception in the 1980s. But as of the start of the hub in 2017, we arranged to have CSLAP operating on all 11 of the Finger Lakes. And so CSLAP operates twice per month in between June and September to give us a total of 8 samples throughout the summer growing period. And we analyze those samples in a high quality laboratory for nutrients and their different forms of nutrient, particularly phosphorus and nitrogen. We look at chlorophyll A, which is an indicator for algae. We used to do more toxin analysis, but we don't do so much anymore. We look at Secchi disk, or the users, the volunteers, look at clarity using a Secchi disk. And we're also very interested in how people are perceiving the water to be. We look at calcium, pH, the acidity of the water, and the conductivity of the water, which is related to how much salt there is in there. And we also look at dissolved carbon. I just wanted to point out to you that not all of these lakes still have so many sample points, but some of these sample points have moved around. The bigger lakes got more samples because they're much larger in volume. And I did want to point out this abbreviation. We'll see this in some later slides, and you can see that it goes from west to east, starting with Conesus as CO, and then Hemlock, Canadice, Honeoye, and so on, all the way through to Atisco over in the east. So some of the CSLAP volunteers, Carl and Ellen, highly valued, Chris Willoughby, and I was very sorry to hear that Mike Parker had passed away. He made a great contribution, and it's very sad, and I was thinking of him. So I've talked a little bit about what the origin of a lot of our data in the summer. Well, what about winter? So our Winter Limnology project started with a simple question. I wonder what frostbite feels like. This is Jack Nicholson in The Shining. Luckily, we've never looked like this at the end of one of our expeditions, but it's come kind of close. But the question that we were really thinking of is, what are we missing? Winter conditions are often not sampled. One, because it's thought that nothing is happening in the winter in a lake. And two, it's just a really unpleasant time of the year to be out, it is thought. And so because of the safety concerns and the logistics, winter has often been overlooked. But there's been, certainly in the scientific world, much more of a focus on winter in the last decade or so. So Michael Twiss and his graduate student wrote a wonderful scientific paper looking at the ways that Great Lakes limnology being the study of lakes, how could that be improved? And they noted that winter data in the Great Lakes is really a major knowledge gap. And they also pointed out that not just from a chemical point of view, but also they wanted to find out more about how that ecosystem functions. And without winter data, there was a significant limit on how that could be improved. We noticed ourselves in the DEC data that there was a really significant gap, and that was identified as early as May 2017. It's also, as we will see, a way of assessing a lake without having to do quite as much sampling in the summer. And one of the reasons for that is that in the winter, as we'll see in some cases, the lakes are really well mixed. There's no stratification at some points, as we will see. And so if you take one sample from the lake, you're taking effectively a really great bulk sample, a sample that is representative of the bulk composition of the lake. So we had lots of water quality data for June to September and almost none, next to nothing for winter. So we set up a program. It was my idea. So if it's good, it's all, you can give me the credit. If it didn't go so well, then I also get the blame. We're doing it on all 11 Finger Lakes. We sample in 3 goes in December, February, and April. So we've been doing it for 5 years. December is often, has been the period where we don't go out and sample. And that's because it comes at the end of the major summer sampling season. And to be honest, I have been less prepared to do December than I have been February and April. We're taking very, very similar samples to CSLAP. And we're also taking Secchi disk depth where we can. We're also, though, taking multi-probe samples. And these are where we're able to lower down on an electrical cable a system which will look at dissolved oxygen, temperature, pH, acidity, and chlorophyll. That's the pigment which is found in algae. And so we can see what the lake looks like as we lower that down. We've also been working with ESF, SUNY Environmental Science and Forestry College, to take a whole series of zooplankton and phytoplankton samples. And so this is what the Finger Lakes in the top right look like in the winter. This is from a satellite, and you can see that we are mostly looking at the CSLAP sites in the north. In the Cayuga, we're looking at the west branch of Cayuga, and you can also see that some of these lakes appear white, and that is because they do freeze over. Even the northern fifth, say, of Cayuga Lake does freeze over parts of Cayuga. When that happens, we will go out on the ice. This is one of Carl Hannafin's spectacular drone shots. This is Conesus Lake. We were quite a lot of people out on the lake that day. That's 1, 2, 3, 4 people out. Usually we would go out with 2 or 3. And we are trekking across the ice, pulling a couple of jet sleds with equipment to the same location that is used in the CSLAP summer sampling, so that they are repeatable. Now, it's not always frozen solid. This is also Conesus Lake. And I forget the year. There was one year where February was starting to get a little bit warm. It had warmed up a little bit. There was water lying on top of the ice. We do have very strict safety protocols where we don't even go out on the ice if it's less than 4 inches thick. I know there are some ice fishermen that would go out when it's 2 inches, but we have a margin of safety. But on this occasion, there was about 2 inches of water on top of the ice, which is kind of a little bit unnerving, but we did manage to sample. Okay, so I've outlined, as a recap, I've outlined how we get our summer data, thanks to the CSLAP volunteers, and we've gone out to try and fill in those gaps with winter data. Now, having outlined all of that, I'm just going to focus right now on the CSLAP data, the summer data, and I'm going to look at the 4 years of CSLAP data that were readily available to me, and I'm going to compare Conesus Lake to the rest of the Finger Lakes and also to all of the CSLAP lakes, 170 of them in New York State. So I've got a couple of these diagrams, and I just want to outline what they all mean. Okay, this is a box and whisker plot. The box here, the line going through it is the mean of the values. So the average value is represented by this line in each box. The top boundary of the box and the bottom boundary are the upper quartile and the lower quartile. So 50% of the samples occur within these two boundaries. And then we have these whiskers, which then go out to, I think, 95 and 5%. So all of the data, or 90% of the data, is found within these two boundaries. And then if there's anything else significant outside of that, then we can show them as these little dots. So, and I'm going to show you along the bottom, we've got Conesus Lake and the rest of the Finger Lakes going from west to east, finishing with Atisco. And this is all of the CSLAP lakes, about 160, 170 of the CSLAP lakes in New York State. All right. So starting off with calcium. Obviously, calcium is the element that gives you, along with carbonate, the hard water in the bottom of your kettle, if you make tea like me. And you can see that Conesus is pretty similar to a lot of the other Finger Lakes, unusually high compared to the other Western lakes. But what does this, and relatively higher than the rest of the lakes in New York State as sampled by CSLAP. What does this mean? Well, I guess you don't have exceptionally hard water, but what it does mean is that you have you do have the ability, or let me put it this way. Zebra mussels and quagga mussels have no problem extracting calcium from the water at these concentrations. Interestingly, over in Conesus Lake, concentrations are low enough that they may be the limiting factor for zebra and quagga mussels. And so we do see many fewer of those mussels in Conesus Lake. So that's calcium. So chloride, we've heard a lot about chloride in recent years. Chloride is increasing generally across the state, and it is probably due to the use of road salt on our roads. But you can see that Conesus is a little bit higher than the rest of the Western Finger Lakes, but it's quite comparable in many ways to Canandaigua and Cayuga. What is noticeable is that Seneca Lake has very high chloride concentrations. And that's probably because of the history, the legacy of salt extraction and brine discharges that took place in the 1970s, I believe. Interestingly, we won't see it because I'm going to focus on Conesus water quality trends, but chloride concentrations in Seneca Lake are decreasing. Then we get on to chlorophyll A, and in some ways this is misleading. Remember that these are averages and these are most of the data here. Conesus is definitely up there with some of the highest concentrations of chlorophyll A in the Finger Lakes. So it is third in terms of a mean after Atisco Lake, and of course Honeoye Lake we know has a very high algae content, and that's reflected in these chlorophyll A concentrations. But interestingly, we do see with Conesus that we have a couple of outliers, and these are quite high concentrations. The highest classification for our quality of water starts at around 8 micrograms per liter of chlorophyll, and above that we would start to classify these waters as eutrophic. That means nutrient rich. So we are starting to see Conesus, or I should say we're not starting to see Conesus. Conesus has recently been on the boundary between mesotrophic, that's middle nutrient levels, and high nutrient levels. Honeoy is certainly eutrophic. Okay. Right, not wanting to miss out on oxidized nitrogen. These are also a set of nutrients, nitrate and nitrite. The difference between nitrate and nitrite actually is just the number of oxygens. So anything in chemistry ending with ATE has 3 oxygens, and anything ending in ITE has 2 oxygens. But the main thing is they're both oxidized forms of nitrogen, which is another micronutrient. In Conesus, as with most of the other Finger Lakes, this isn't the limiting nutrient. Phosphorus is the nutrient which is in the shortest supply. But you can see here that most of the lakes west of Seneca, or all of the lakes west of Seneca, have got means below about 0.2, that should be 0.2 milligrams per liter. Sorry, there is an error in this y-axis. This is 0.2 milligrams per liter. Interestingly, the rest of the Finger Lakes to the east have really got quite high concentrations of nitrogen, oxidized nitrogen, in the summer. As we found out from our winter sampling that these concentrations drop dramatically during the winter. Sorry, the other way around. They have high concentrations in the winter and then they drop during the summer. So these are the minimum concentrations. Getting myself a little bit in a twist there, but let's move on to phosphorus. This is a really interesting one. So you can see that the mean for phosphorus is second only to that for honeoy. And once again, this puts Conesus Lake along this boundary between mesotrophic, middle quantities of nutrients, and eutrophic, which are high quantities of nutrients. But interesting, you can see that the Conesus mean is about the same as the mean for those CSLAP lakes in New York. Now, I've compared Conesus to the rest of the CSLAP lakes, and those were using 4 years of data. What I'm going to do now is put that into a context, into a series of time series where we show summer and winter data next to each other. And let me just introduce this plot, because we'll look at some very similar plots in the next couple of slides. So we've got concentration on the y-axis going vertically. On the horizontal axis, we've got dates going from 2017. So these all start off in the summer and going to, I think they finish off around April 2021. So the summer data is the green squares, the winter data are the blue circles. And apart from those two factors, the fact that it was taken in summer and winter, there is no other difference. They were taken in exactly the same way, using the same kind of sampling equipment in the same locations and analyzed at the same labs. The only difference, I would say, is that in each February, the samples were taken through the ice. Now, you can see that the first year that we went out on the ice, we got these really tremendously high concentrations of chlorophyll. And this was a real surprise to us. And we thought, wow, this is so much higher than what's going on in the summer. There's something really interesting going on. Well, it just goes to show you that you need more than 1 year of data, because in subsequent years, we've been unable to recreate those very high chlorophyll concentrations, and some of them in the winter have been really quite low compared to the rest. Nevertheless, I do think that these are quite significant, and I suspect it's to do with patchiness of algae blooms underneath the ice. You can see that once again, the eutrophic level of 8 micrograms per liter, which is shown by this thin red line, is exceeded in many cases during the summer, but it is on occasion, it's also exceeded in the winter. Okay, so that was chlorophyll. And I should say that these are all samples that are taken at about 1.5 meters depth below the surface or below the ice. So 1.5 meters is about 4.5 feet. As we'll see later on, the concentrations of chlorophyll do change though when looking at depth. And we'll look at some of those graphs in a little bit. Right, total phosphorus, that very important nutrient. Once again, we've got the guideline value here of 20 micrograms per liter. It's a guideline, it's not a legal enforceable minimum or anything like that, or a maximum. DEC did some work a couple of years ago which looked at how concentration of phosphorus aligns with how people perceive their lake. And this 20 micrograms per liter was the guideline value that was derived. So you can see that there, once again, there's no great difference in between summer and winter values. I haven't tried to put a regression line through this, but you could draw your own conclusions from that. And there's still plenty of work to be done in looking at all of this data. Total nitrogen, though, is a really interesting story, and we have seen this across the Finger Lakes. What we're seeing is, this is slightly messy data, as you always get with natural sampling, but what we're seeing is that nitrogen actually decreases during the summer and then increases back up again in the winter, and down again in the summer, up, down, and up. And this is to do with the way that nitrogen is used up by organisms in the lake, but it's also turned from a soluble nitrogen, like nitrite and nitrate, into gaseous nitrogen, that's N2, and that's able to then escape into the atmosphere. So we see this I think, quite clearly in Conesus Lake. We will also see it across the rest of the Finger Lakes. And then finally, for the time series, I did just want to show you, even though we're not taking chloride concentrations in the winter for some reason, and I'm going to have to look into why, people have been very interested in seeing what chloride is doing in terms of a trend. And I think you can pretty much see, let's just say that chloride influences how electrically conductive the water is. and we can measure that with a parameter called specific conductance. You can see, I think, pretty clearly that specific conductance is increasing over time. Now, I'd like to have had some longer term measurements in here, but I didn't have time, unfortunately, to include them. But we do know that chloride and specific conductance are increasing across the state in many water bodies. Okay, so all of those were taken at 1.5 meters. Now, what do these lakes look like as you lower down your instrumentation? Well, this is a picture of us preparing to do it. This is out on Conesus Lake. Once again, thank you to Carl for taking this picture, and my colleagues Stephanie, June, and Tony and Bree from Region 8 Fisheries. We've drilled a hole here, and we've scooped out all of the ice. This particular time we went out on the ice on Conesus was particularly scary because it was black ice, and it was very difficult to see how thick it was. It felt almost like it was paper thin, but in actual fact, it was 8 inches thick with no snow on top. And so you just felt like you were floating in the air. There was only 8 inches of ice between us and oblivion, but in actual fact, it was perfectly safe. So here's a couple of things that I've lumped together. The 4 eastern Finger Lakes, Conesus, Hemlock, Canadice, and Honeoye, with the far eastern Finger Lake of Atisco. And the reason that I've done that is that these were all taken during a period of ice cover. And you can see, hopefully very clearly, that Conesus here is the circle with the gray filling. And so Conesus Lake, there was a certain amount of temperature stratification, so that we had cooler water closer to the ice, and we then went into warmer water. And this is obviously an effect due to the way that water actually, let's see if we can remember, water continues to shrink from sort of room temperature down to about 4 degrees centigrade. That's about 40 degrees Fahrenheit. After that point, it starts to increase in buoyancy, and until it eventually freezes, obviously at 0 degrees centigrade. So what we find is that below 4 degrees centigrade, we tend to have this inverse stratification where we get warmer water. It's still pretty cold, but it's warmer than at the surface. So we get warmer water at the bottom of these lakes. There's really not that much change. I mean, 2.5 degrees centigrade to 3 degrees centigrade in Conesus Lake might seem not very much, but we think it does have some environmental significance. Although the main significance of the conditions underneath the ice is that they're very stable. They're not subject to wind. There's going to be very few seiches. There's going to be no currents. And we think that that enables algae to use some of their innate buoyancy, or some of the species at least, to really hang out in their preferred areas. So here's a really surprising result that we found. This is from February 2018, where we did get exceptionally high concentrations of chlorophyll. Remember, that's the green pigment that you find in algae, which then dropped off considerably, but still in Conesus Lake, there were still quite high concentrations of chlorophyll during the winter underneath the ice. Much less so in the rest of the western lakes. Likewise, we also saw this peak in oxygen, in dissolved oxygen just below the ice in Conesus Lake. And that's probably because of the oxygen which is being produced by algae through photosynthesis. Drop down to more normal concentrations at greater depth. And it is interesting that some of the other western lakes really start to see a decrease, significant decrease in their oxygen concentrations with depth. Now, just to compare that to the open water lakes of Canandaigua, Keuka, Seneca, Cayuga, Owasco, and Skinnyakulas, you can see that there's very little change in temperature. For instance, Seneca Lake was, 3.8 degrees centigrade from basically the top to the bottom. And so what this is showing us is that these are well mixed lakes, and any algae that happens to be in this lake is going to be tumbled from the surface to the bottom and back again, and will be out of the photic zone. That means the zone that gets sunlight, whatever small amount of sunlight is available to them. It's going to be only in that photic zone for a small amount of time before it's mixed back into the rest of the dark lake. And because of that, we see very low concentrations of chlorophyll in these open water lakes in the winter. Likewise, their dissolved oxygen concentrations occur in a very small range, between 10.5 and 11.8 or so. And those would be typical of that kind of cold water exposed constantly to the atmosphere. So I did mention right at the beginning that we had a winter plankton program. I'm just going to talk a little bit about that. We took samples through the ice and in open water for the Environmental Science and Forestry College. It was a very simple sampling protocol. We took this plankton net with a little cup on the bottom and drop that down to about 2/3 of the depth at each site. And then as we pull the plankton net back up again, the water sieves out through the netting, and it traps the plankton, the little zooplankton in the net, which we then wash down into the cup. And you can see this is Tony on the left and Bobetta Davis, who is the master's degree student who then went on to identify and actually count all of these little zooplankton from each of the lakes over the last 4 years. So there has been a previous study which looked at zooplankton and phytoplankton from the Finger Lakes in the summer, and our aim was to compare the two to see if there are really significant differences between the two. We'd expect there to be. And we also wanted to collect data for potentially an ecological model. And the model would then use our information about, because basically zooplankton and phytoplankton are at the bottom of the food chain. They are eaten by small fish, the small fish are eaten by big fish. And we don't really, in New York State, as far as I know, have an ecological model to relate all of those levels of the food chain together, and also to relate it to our nutrients. So, and one of the reasons is that we don't have the data. So this was part of that effort. Once again, you can see that we were out on, this may actually be a Tisco lake, but you can see that, boy, these lakes are highly productive even in the winter. What we're looking at here is a filter paper from our vacuum apparatus when we're filtering water. Quite often in the summer, you filter a half a pint of water and you don't really see much. In this case, in the winter, we were seeing this kind of brown goop, and that's all phytoplankton. Now, what I'm showing you here is actually the difference between February and April concentrations of chlorophyll, which are associated with different kinds of phytoplankton. And we have taken this from an instrument called an algae torch. It uses LED light and photosensors to work out what kind of algal community we're getting. And you can see we were once again blown away by the concentrations of chlorophyll. And in this case, they were associated with green algae. And this was in February. Compared to the rest of the Finger Lakes, it was much, much higher. Now, by the time April came around in that same year, concentrations had dropped off, and we seemed to have a change to diatoms. And these are more silica-based. So I'm not giving you a very sophisticated analysis of our results, but what I wanted to really get you to understand is that these lakes are really active during the winter, especially the ice-covered lakes. And, you know, we're definitely getting away from the idea that nothing much is happening in these lakes in winter. I did take a couple of photomicrographs of the organisms that we found. These are phytoplankton. These particular star-shaped ones are known as Asterianella. You can see that there are a lot of Asterianella in the water from February. And we also see plenty of zooplankton feasting on these blooms as well. Now, Bobetta Davis has not yet finished her master's degree, but when it is finished, I'm sure that it's going to be a fascinating look at life under the ice in the Finger Lakes. All right, so coming towards the end. So has this been an exercise with a point? Well, I would say yes, it has. It has been a useful exercise. So previously, in the 70s and 80s, winter and spring concentrations had historically been a measure of water quality. And once again, you can see the reason is because those lakes are thoroughly mixed usually, and they give you a really good idea of what the average concentration of phosphorus is. Phosphorus with the element, the symbol of P. So we've seen that external phosphorus loads go into our lakes, often in the spring thaw. Some of that phosphorus is available to it's available to the biology, the phytoplankton in particular. And then that total phosphorus in the winter is then available to power a lot of chlorophyll activity in the summer. And once we have a lot of chlorophyll in the summer, that's going to decrease our Secchi disk depth and our clarity. And in 1978, these guys, Oglesby and Schaffner, took the winter phosphorus and found that it could be related mathematically with quite a high degree of confidence to the summer chlorophyll concentrations. Now, I've tried to do that with current data with mixed success. Some years it seems to be a very, very good relationship, and other years, for whatever reason, it's not so good. So I can understand why we've gone away from measuring total phosphorus in the winter and trying to just unilaterally declare this is what we think the chlorophyll A is going to be in the summer. What we do now do is measure chlorophyll A in the summer. But you can see here that they are quite closely related. Admittedly, this is a log plot, so we've got logarithmic scale on both axes, but you can see that we've got quite a nice relationship, a linear relationship between spring total phosphorus, that's the phosphorus that's collected in April, and the summer chlorophyll. And what that means is that this could be used for prediction. We could go out and take a sample in the spring, in April, and using this kind of relationship, we can say, you know, a value of 10 milligrams per cubic meter in the spring is likely to give us a value of 3 milligrams per cubic meter in the summer. So those are powerful relationships if we can make them stick. We've also found that the winter data has been very useful in terms of modeling. Previously, when lake models were run, they had lots of data in the summer, but the models were unconstrained, meaning there was no data to compare them to in the winter. So we've been able to use some of this data in, for instance, Canandaigua Lake, and I know that we've also used it in Owasco Lake. So what's the future of our project? We're continuing to do data collection. I'm fully expecting us to be out on the lakes this winter, and we are definitely doing further analysis. We want to definitely look at this kind of relationship that has been postulated in the past and see if there's been any significant changes from past relationships. And it would be very interesting to see if we could assess water quality just based on winter data. And that is still a very significant piece of work which needs to be done. Okay, I don't have a watch with me, but I think I've probably talked enough. So thank you very much for your attention, and I will finish it there.
Any questions? You can type it in the chat bar or hold your space bar down.
I got a question there for how far down. Sorry, I didn't see that. If the author wants to ask that question and perhaps clarify.
I think you answered it, a meter and a half.
Okay, I got a question there from Holly. Is Conesus a healthier lake than others? Healthier, that's a term that's quite broad. So, you know, it is what it is. I think I've laid out all of those concentrations, the nutrients. It's a great lake for fish. Obviously, you've got a good base for the food chain in Conesus Lake. You know, I think the chloride concentrations are still well below the maximum concentration limit that would be required in drinking water. So I think in some ways, Conesus is a healthy lake. The other part of the question was Secchi disc method. That is, sorry, I should have explained that. A Secchi disc, which was invented by a Jesuit priest in the employment of the Pope about 200 years ago, when he was looking at trying to measure how clear the lagoon in Venice was. It's an 8-inch wide black and white disc. Black and white is in separate quarters, and it's lowered down on a tape measure until the person in the boat can no longer see the disc once it's disappeared. And that is the Secchi disc depth. It's a super simple way of measuring clarity, and it's standardized all around the world. So the deeper your disc goes in the water, the more clear your water is. I think that that's how I would explain a Secchi disk depth. Have there been any studies on neurotoxins in algae blooms? Yes, absolutely, Jean, thank you for that. There certainly has. And so there are different kinds of toxins in cyanobacterial blooms. Some blooms have no toxins at all, not that we can detect. Others have a variety of different toxins. Microcystin is one that is commonly found in a toxic bloom, and that's a hepatotoxin, which attacks the liver. And a much rarer one is known as saxitoxin, and that is a neurotoxin. So a question, when plotting chlorophyll versus depth relationships under the ice, are you accounting for the inverse relationship between fluorescence and temperature? Right, Mike, fantastic. We are taking the chlorophyll concentrations from the algae torch uncorrected. So I'm not sure that the temperature variation is going to be significant, especially since we are looking at more or less isothermal lakes. So lakes that have got very little difference in temperature. You know, absolutely, we're talking about 1 or 2 degrees centigrade. I think what might be more significant is the variation in light as we go down through the water column, because of what's known as photochemical quenching. Not to get too technical, but I'm showing uncorrected plots here. But Mike, that's a great point. Thank you for pointing that out. You say the lake is somewhat healthy. Are there any cause for concerns about the general health of the lake? The reason that I didn't want to say it's healthy or not is that what I've observed over the 5 years that I've been with DEC is that there's a variety of different uses for a lake. Fishermen want lots of fish, and for there to be lots of fish, there's, you know, the more phytoplankton and zooplankton there are, the better in some ways, and that's that can result from very high nutrients. Whereas there might be other people who want to have a completely clear lake that they can see the bottom of, that they can swim with no weeds and anything like that. And those kind of lakes are called oligotrophic lakes. They have very low nutrients. And so those two kinds of people would have different perceptions of what a healthy lake is. So that's the reason why I didn't want to give a particularly robust answer on that one. From a health point of view, I know of no reason not to drink treated water from Conesus Lake.
Any other questions? Don't hear any of those. One more from Jean.
Oh, does chlorine kill the cyanobacteria? You know what, I think that thinking is changing around this topic. 5 years ago, it was thought that chlorine didn't kill cyanobacteria. But for instance, Syracuse has a water supply from Skaneateles that is untreated. It's only one of 2 water systems in the whole state which doesn't have significant treatment on it, the other being New York City. And because of that, once they started to see increased concentrations of cyanobacteria, they didn't have a treatment method. The only thing that they do to their water is add a little bit of chlorine as a protective measure. Syracuse did add chlorine to its water supply, and they didn't detect toxins in the water supply in their distribution system. This is me from memory. And so I think the jury is still out on that. It's outside of my expertise. So I would suggest looking that topic up further from more reliable sources than me. Sorry, I can't be more definitive than that.
Those, I want to thank you for your continuing participation. I think this is 5 years you have presented to us. So we really appreciate your help and education. I'll be sending you a certificate of appreciation. And to the folks on the call, I will send out tomorrow morning a survey looking for your comments about tonight's topic, as well as any ideas you have for future topics. We are in the current planning session of planning our 2023 schedule. So now's a real good time to give us your ideas on what you want to hear in the future. With that, we'll close the meeting. And I thank you all for attending. Our next event is the Rainbow. Watch for the fire and sign up early.